Hello, Mr. Biter here with the notes on chemical reactions. The words to know are chemical equation, reactants, products, law of conservation of mass, catalyst, chemical reaction, and concentration. Key questions: what is a chemical change? What are the parts of a chemical equation and what can they tell us? What evidence shows a chemical reaction is taking place? How can the rate of a chemical reaction be changed? What is the law of conservation of mass? So what is a chemical change? Well, a chemical change is also known as a chemical reaction. And in a chemical reaction, just like a chemical change, a new substance is produced. A new substance is formed, but all the elements that are present at the beginning are also present at the end. They're just rearranged. You might have new compounds and new rearrangements of those elements altogether. So chemical bonds, therefore, are formed or broken apart during a chemical change, also called a chemical reaction. We show a chemical reaction using a chemical equation. In a chemical equation, we have the reactants on the left side, and we have the products on the right side. And we represent the number of molecules, if you remember, using a coefficient. And this says that there's this many molecules of it after it. So 2H2 means there's 2 H2s for a total of 4 H's on this side, and we'd have a total of 4 H's on this side, 2 on this side of O's, and 2 O's, oxygens, on this side. What evidence shows that a chemical reaction is taking place? Well, if we mix two things together, for instance, we'll notice bubbling maybe. That shows a gas is being produced, like if you mix baking soda and vinegar. A temperature change might occur, such as might occur in a ice pack that you have to break and you shake it and it gets cold. All right, that's energy being either taken in or out. That's energy being pulled in. It's an endothermic reaction if it's that ice pack. We could also say a color change. We mix two things together and there's a change in color. It turns from clear to red. And sometimes we have what's called a precipitate is formed. We can mix two liquids and then a solid is produced when those two liquids are mixed together. These are examples of chemical changes. We talked about the instant ice pack here. We break it, mix it together. We know there's a chemical reaction occurring because there's a change in temperature. This is zinc and hydrochloric acid. We can see hydrogen gas being produced here, these bubbles. Now, how can we change the rate of a chemical reaction? This is useful, and this happens in our bodies all the time. And we can increase the rate of chemical reactions by increasing temperature. We can also increase that rate using surface area, concentration, and a catalyst. Now you're going to see a video that explains this and a lot more in better detail.
Meet our chemist, Harriet. She has a chemical reaction that needs to occur more quickly. Our chemist has some processes at her disposal that can help her speed up her reaction, and she knows of 5 ways. And to remember them, she thinks back to her days as a high school student, and the day she got a date for the dance. Harriet was in high school studying between classes. She had lost track of time and was going to be late to class. Unbeknownst to her, Harold, who was just around the corner, was running late too. They both sprinted to class, and as it happened, sprinted directly into one another. Now, this was no small collision. They ran squarely into one another in such a way that he knocked the books right out of her hand. "I'm sorry," he said. "Let me help you with your books." He kindly helped her recollect her belongings and politely offered to walk her to class. And you'll never guess who went together to the dance later that year. Yep, those two. So as we can see from this example, the key to getting a date for the dance is to collide with someone and knock the books out of their hands. Now, you're probably already aware that not all collisions lead to dates for the dance, thankfully. The collisions must have 2 important characteristics. 1, correct orientation that allows books to be knocked from one's hands, and 2, enough energy to knock the books out. Shortly after this incident, Harriet decided to tell me, her chemistry teacher, all about it. I noticed some interesting parallels between her story and chemical reaction rates, which happened to be what she was studying in the hallway the day of the collision. Together, we decided to set out on 2 missions. Harriet wanted to help all chemistry students and chemists remember how to speed up the rate of chemical reactions, and I, being the nice guy that I am, decided to make it my mission to help create educational environments in which more book-dropping collisions can take place to increase future chemists' chances of getting a date for the dance. In order to facilitate this improved dance date-getting process, I propose 5 changes to all schools that parallel Harriet's 5 ways to increase chemical reaction rates. First, I propose that we shrink the size of the hallways. This will make it more difficult to safely navigate the hallways and will cause more collisions than in larger hallways. And by increasing the number of collisions, we increase the likelihood that some of those collisions will have the correct alignment and enough energy to create a date to the dance. Now, chemically speaking, this is equivalent to lowering the volume of a reaction vessel or a reaction mixture. In doing so, the individual particles are closer together and more collisions will occur. More collisions means a greater likelihood that collisions with the appropriate energy and configuration will happen. Second, I propose increasing the overall population of the school. More students equals more collisions. By increasing the number of particles available for collision, we create an environment where more collisions can take place. Third, we must reduce the time allowed between classes. Heck, let's just cut it in half. In doing so, students will need to move more quickly to get from one class to the next. This increase in velocity will help make sure collisions have the appropriate amount of energy necessary to ensure book dropping. This is analogous to increasing the temperature of the reaction mixture. Higher temperature means particles are moving faster. Faster moving particles means more energy and a greater likelihood of reaction causing collision. Fourth, students must stop traveling in packs. By traveling in packs, those students on the outside of the pack insulate those in the middle from undergoing any collisions. By splitting up, each student has more area exposed that is available for a collision from a passing student. When particles travel in packs, the surface area is very small, and only the outside particles can collide. However, by breaking up the clumps into individual particles, the total surface area is increased, and each particle has an exposed surface that can react. Fifth, and finally, we hire a matchmaker. Is this colliding and book dropping too violent? Is there an easier way to get a date that requires less initial energy? Then a matchmaker will help with this. The matchmaker makes it easier for a couple to get together by coordinating the match. Our matchmaker is like a catalyst. Chemical catalysts function by lowering the activation energy. In other words, by lowering the energy required to start a reaction. They do this by bringing 2 particles together and orienting them correctly in space so that the 2 can meet at the correct configuration and allow a reaction to take place. So, to sum up, if a future chemist wants a date for the dance, he must collide with another person and knock the books out of their hands. And if a chemist wants to make a chemical reaction occur, the particles must collide in the correct orientation with an appropriate amount of energy. And both of these processes can be accelerated using the 5 methods I've described.
What is the law of conservation of mass? Well, we saw before there is such a thing as a chemical equation, and it shows that there are reactants and that there are products. Here we have reactants on this side, we have products on this side. And the law of conservation of mass says we have to have the same amount of stuff before and after, because matter, the elements involved in the reaction, aren't being created or destroyed. They're not just coming out of nowhere or disappearing. They're going to be there for that reaction before and after. All right, so when we have the law of conservation of mass and we know that there's going to be the same amount of stuff, the same amount of matter, the same elements before and after, we know we can balance that equation. All right, and we know how many elements, how many atoms of each element are on one side and how many atoms of each element are on the other side. And we know, because we know how to use chemical formulas, how many on each side there are, because we can count them up. So you're going to try to balance these equations here. All you're going to want to do is substitute the values in. Here, for instance, N2, there's only one N, or 2 N's on this side, 1 N on this side. So if we put a 2 here, that'd make 2 N's on each side, which is good. But then there's 2 H3s, which means there's 6 H3s, so we'd have to add a 3 here to make 3 times 2, 6 hydrogens on this side. So you put in the coefficients in the beginning here, and just through some trial and error and simple multiplication, you can try to figure out how this works and how we can balance the equations. Give it a try. You might not be able to do all of them, but especially those of you that are better at math, this is kind of like a fun puzzle to try to figure out. Good luck.